Section 8.1 is on inverse variation. An inverse variation equation has the form of xy equals k, or y equals k over x. In other words, we divided both sides of this equation by x, where k is called the constant of variation and k is not equal to 0. When two quantities vary inversely, as one of the quantities increases, the other decreases proportionally. Contrast this with direct variation, which you're more familiar with is y equals kx, or k is equal to y over x. Whereas one quantity increases or decreases, the other increases or decreases proportionally. Let's take a look at an example here. Is the relationship between the values in each table direct variation, inverse variation, or neither? If it is a variation relationship, then write an equation to model that relationship. So in our first example here, we have x and y values, so 1 and 52, 2 and 34, 5 and 4, 6 and 2. So the easiest to figure out is it inverse variation? If it's inverse variation, then x times y is going to equal a constant value. So let's take a look at our table. 1 times 52 is 52. 2 times 34 is 68. So x times y does not equal a constant. Therefore, it's not going to be inverse variation. Let's see if it's direct variation. That would mean that x times a constant, times the same number each time, is going to equal y. So x, I have to multiply it by 52 to get 52. Okay, 2 times 17 gives me 34, so this is not direct variation because I cannot multiply each x value by the same constant value and get y. So this is not direct variation. So that, sorry about that. So that means that this one is going to actually be neither. Oops, doing it again. Sorry about that. All right, let's take a look at B here. So here I have my x values, here I have my y values, and let's check and see if it's inverse variation. So when I do 0.2 times 0.8, I get 0.16. When I do 0.4 times 0.4, I get 0.16. 0.5 times 0.32, it sure looks like that x times y is a constant value. So x times y is equal to 0.16. So this is going to be an example of inverse variation. And my formula, I actually kind of like to have it solve for y. So we'll divide each side by x. So the equation that models that relationship is y equals 0.16 over x. Let's take a look at another example here. This one says, suppose x and y vary inversely, so I know that there's going to be an inverse relationship here, and x is equal to 2 when y equals 8. We need to write a function that models this inverse variation. So I'm going to start with xy equals k, and plugging in 2 for x and 8 for y. That gives me my k value of 16. So my function is xy equals 16. Or solving that for y equals 16 over x. Actually, either of those will work fine. Okay, now we need to graph this function. So basically, I'm looking for pairs of numbers that multiply to 16. Because notice, x times y has to equal 16. Well, I could do 1 and 16, but that won't fit on my graph. So I'm going to do 2 and 8, 4 and 4, 8 and 2, and then I also need to have some negative numbers. Negative 2 times negative 8, negative 4 times negative 4, and negative 8 times negative 2. So that's going to give me something that looks like this, and 4, 4, and 8, 2. And then when I do the negative values, negative 2, negative 8, negative 4, negative 4, negative 8, negative 2 gives me, oops, kind of missed the point there, that part of it. So that's what the graph of an inverse variation equation looks like. And part C here says, what is y when x equals 4? So I have y equals 16 over x. So when x equals 4, y also equals 4. Here's another example. Your employer decides to hire extra help to deliver newspapers during the holidays. The table shows the number of employees who delivered papers each week and the time needed for delivery. So when there were 2 employees, it took 100 minutes to deliver. When there were 4 employees, it took 50, and so on. So these are going to be my x values. These are going to be my y values. What function models this situation? Well, this is inverse variation, so x times y is going to equal a constant, and I can see by multiplying that's 200. So I could do xy equals 200 or y equals 200 over x. In other words, the number of minutes is going to be 200 divided by the number of employees. Part B, how many employees should there be to deliver newspapers in at most 40 minutes each week? So in other words, if my number of minutes is 40, how many employees do I need? So plugging it into the formula, 40 for y, 200 over x. X is going to be equal to 5, so I need 5 employees to get the papers delivered in 40 minutes at most each week. Sometimes one quantity can vary with respect to 2 or more quantities. This is called combined variation. When such a variation is direct, it's called joint variation. Here's a little text box from your textbook. So different types of combined variation. If we say that z varies jointly with x and y, that's going to be a form of direct variation, so z is going to equal your constant of variation times x times y. Jointly with x and y is going to be times xy. If z varies jointly with x and y, so again I'm going to have x times y, and inversely with w, remember inverse variation has the variable in the denominator, so that's going to be z equals my constant k times xy all over w. And then if z varies directly with x and inversely with the product wy, that's going to be z equals k times x, because that's a direct variation, and then inverse is going to put that product wy in the denominator. And let's take a look at one more example that's going to use this type of combined variation. The volume of gas varies directly with its temperature and inversely with the pressure. Let's start with that. Let's not worry about the numbers right away. So write an equation that models this relationship. So the volume of the gas is going to vary directly with the temperature. So I don't know yet what my constant of variation is, but I do know that it's going to vary directly with the temperature and inversely with the pressure. Direct goes on top, inverse goes on the bottom. Now I need to find the value of K, and that's where I'm going to use the second part of this problem. The volume is 100 cubic meters when the temperature is 150 Kelvin and the pressure is 15 pounds per cubic centimeter. Okay, so that's going to be 100 equals K times 150 over 15. Solving that, K is going to be equal to 10. So my formula is going to be, the equation that models this is going to be the volume equals 10 times the temperature divided by the pressure. Now I'm going to use that formula to answer part B here. What is the volume when the temperature is 250 Kelvin and my pressure is 20 pounds per square centimeter? So my volume is equal to 10 times the temperature divided by the pressure, or my volume is going to be 125 cubic meters. So in this section we took a look at inverse variation, how to write inverse variation equations, how to solve them, and took a look at different types of joint variation.